This is an experiment. I'm going to try doing an extra example that we don't have time for in class on the board here in my office. It's a little cramped, and I know the resolution isn't the best, but I want to see if doing this recording and putting it somewhere where you can refer back to it over and over could be a useful way of doing these things. I'll be interested in seeing what your feedback is once we do it. So to begin with, the example I want to talk about is another continuous charge distribution example based on the same things from this little handout that we've seen in class on continuous charge distributions. The example I want to look at is the example of a hollow spherical shell of charge with charge evenly distributed across it. Surface charge density is sigma. And what I want to do is center that sphere of charge at the origin of my coordinate system, x, y, z, and then measure the charge, measure the electric field rather, at some target point z along the z-axis, at some point a distance z up along the axis away from the center of the sphere. That's my goal, and I want to calculate this out using Coulomb's law and the standard continuous charge distribution techniques that we've learned. So, some setup things. I've already labeled the target point and drawn my picture here, always valuable things to do. To describe the points on the sphere, well, I guess I should start going through the official steps for continuous charge distributions. I've drawn the picture and chosen the coordinate system. I'm going to divide my charge into small pieces dq, and in particular, the small pieces are going to be just tiny little segments of the surface of this sphere. So that's my little dq right there. dq is just a little chunk of the surface. We'll describe it in math later. And I know, based on that since I've got a little point-like charge that's small enough to be a point, that I can use just the standard Coulomb's law formula for that little dq. Its contribution dE vector to the total electric field is just Coulomb's law, 1 over 4 pi epsilon naught dq over script r squared, script r hat. All right, we've set that up. We're going to need to work out what script r vector is soon. But before we do that, I want to go and think about symmetries a little bit. Notice that this whole system can be, including the target point, can be rotated around the z-axis without changing anything. So by doing that rotation, that means that I won't have any x or y component in the end. Now every individual point here will most likely have an x and a y component of the electric field that shows up. But in the end, I won't have that. In the end, I'm only going to have a z component. So I know only EZ, oh, this pen is dying, only EZ will count in the end. So I'll just keep track of that. Once I'm doing my calculations, I can ignore the x and the y components of the electric field when I go to add things up. All right, so next I'm supposed to use a density, the charge density sigma, surface charge density sigma, to write this dq in terms of geometry. There, I need to remind myself, we said spherical coordinates, right? That means theta is the angle down from the z-axis. And then if I project my vector down to the xy plane, phi, as usual, is my angle away from the x-axis that I am there. Standard spherical coordinate stuff. So if I want to write my dq in terms of these things, dq is going to be equal to sigma dA, and I'll call that dA prime. Remember, if we're adding up source charges and if we're adding up a bunch of different source charges, the source point we're going to call r prime, not r. So I'll label these as theta. In fact, I should probably even label over here as theta prime and phi prime, since those theta and phi coordinates are labeling the source point rather than the target point. Well, that'll come into play as we go through this. So dA is going to be my little element of area, and we know how to do this, right? We know that dA, this is sigma times dl theta prime times dl phi prime. We've seen that notation before. That's just our length element for spherical coordinates. Well, this whole sphere has a radius capital R. That was the premise of it that I have written here. So I know this is equal to sigma times r d theta prime times r sine of theta prime d phi prime. That's my that's what I plug in for my length elements. So in total, this is sigma r squared sine theta prime d theta prime d phi prime. That's my charge element that goes into my dE vector. And hey, we have now finished the first side of this handout. So we flip it over and we go on. We write the electric field dE vector due to dq in terms of the geometric variables. So we need to figure out, in particular, this is the point where, sure, we know dE vector in terms of script r, but this is where we actually need to write down what that script r turns out to be. So let's figure that out. We know, by definition, that script r vector is our target point r minus our source point r prime, both as vectors. Well, the target point is really easy. That point is z hat is my target point. My source point, well, I need to use spherical coordinate stuff, right? This is going to be minus my source point. And let me point out, when I take the integral over dE, when I do that integral, I need to make sure that my components of dE are x, y, and z, not r theta and phi. I don't want the e theta and e phi stuff because r theta and phi aren't going to be the right coordinates to, r theta and phi are the right coordinates to do the integral to add up different points. Remember, if I were to do an integral of the r hat component, that would be adding up r hat components at different places, but then I'd be taking a vector that was r hat here and adding it to a vector that was r hat here, which are actually totally different vectors. I can't just add those coefficients. The only safe thing to do if you're integrating, even if you're integrating using spherical coordinates as your d theta and d phi things, even if you're doing that, the only safe way to integrate a vector is to integrate in Cartesian components, because those are x hat, y hat, z hats that every point can agree on. Okay, so I want to write this in Cartesian as my punchline there. So my x hat part, well, I'm just going to do the standard spherical coordinate business. R times sine theta prime cosine phi prime x hat plus r sine theta prime sine phi prime y hat plus r cosine theta prime z hat. That's my spherical coordinate business. Now, we can go through, we've got that r vector. We know in the end that the only parts that are going to matter for us when we're adding up, when we look at the r hat, the direction part of dE, are going to be the z hat parts, because we know the x and the y direction parts will cancel out in the end. Each individual one's not zero, but they'll cancel out. So the parts that we'll care about are this and this. And so we'll come back to those eventually. But for now, we've got this. Let's figure out the length of this, because that's the other piece that we really need down here. We need to know script r magnitude. So script r, all my markers are dying, is just the magnitude of script r vector. And, okay, to do this, you could just be clever and use some geometry, looking at what that is, use the law of cosines, all that. I'm going to just plug through it because, hey, you may not know the law of cosines off the top of your head. I want to show you how to do it. So, well, hey, it's the square root of, it's dying too, curses. My x part is r sine theta prime cosine theta prime squared plus r sine, my y part, r sine theta prime sine phi prime squared plus, here's my big z part, z minus r cosine theta prime squared. That's all under my great big square root sign that shouldn't have run out of ink but did. So that's all under there. Now if we work this out, we can simplify things kind of nicely with this. Notice, for example, that these first two, I get a, oh, that's supposed to be a phi prime. My second one, obviously. These first two, I get a cosine squared of phi plus sine squared of phi prime. And those add up to 1. So this will give me the square root of r squared sine squared theta prime. And again, cosine squared plus sine squared phi prime gives me 1. So those just cancel out, or they combine. Plus, let me multiply this out. Z squared minus 2rz cosine theta prime plus r squared cosine squared theta prime. All that under my square root. Now compare the first and the last terms. That's sine squared plus cosine squared of theta prime this time again. That adds up to 1. So they combine. This whole thing is just the square root of, I should change colors. I should get new markers is what I should do. Let me write this in green since that's been reliable so far. This should become the square root of r squared plus z squared minus 2rz cosine theta prime. All right, that is exactly the law of cosines, if you know the law of cosines, so we could have skipped to this point, but it's nice to see that it comes out from our formalism. So in particular, if I were to write r hat, it's r vector divided by r, script r vector divided by script r. We only need the z component, so I'm going to go ahead and call that script r z, the z component of r vector, over script r. I guess this is script r hat z is script r z over r z hat, if I want to keep the notation right. This ends up equaling, what do we have? Well, z minus r cosine theta. R cosine theta prime, rather, over this square root of r squared plus z squared minus 2rz cosine theta prime. Okay, so I've got all those pieces that I'm going to need. In particular, my r hat, I now know the part of it I care about, the z component of it. My script r, I know what that is too, it's just this law of cosines thing. And my dq, I have written down up here. All the pieces I need for dE are now written down in terms of variables that we can use. So let's clear some space and plug those in. And again, I'm only going to write down the z component. I'm only going to write down, well, I know, DEZ, I'll say. I'm only going to write down the z component. The x and y components aren't 0. I don't want to ever claim the x and y components are 0. I just know that when I do the integral, in the end, they must come out to 0, so I'm ignoring them. So DEZ equals 1 over 4 pi epsilon naught times my dq was sigma r squared sine theta prime d theta prime d phi prime over script r squared, but actually that's going to be times, that's going to be times rz over script over script r. So I'm going to write this over script r cubed, get all the script r's together. So that's r squared plus z squared minus 2rz cosine theta prime all to the 3/2 power times, I still need to get the direction part in. Okay, I'll just put the direction part in. Times this part times z minus r cosine theta prime over the square root of r squared plus z squared. Oh wait, I already did the square root. Haha, right. Let me just get this right. So times z minus r cosine theta prime. There we go. I don't need any other square root. I already incorporated that into the 3/2 over here. So there's our DEZ component. Now all I have to do is integrate this blasted thing to get my actual z component. That's our next step, right? Is integrating DE to put this all together. And let's see what we can do. The only things that are variables are the primed variables, theta prime and phi prime. So sigma and r squared can pull out. Z is also a constant if that ever shows up. I get the integral, let me just be very clear about this. I get an integral d theta prime, and it's the whole sphere, so from 0 to pi. Integral d phi prime, and that's the whole circle, 0 to 2 pi, of, now this whole big thing, sigma r squared over 4 pi epsilon naught. These are all constants that I'll be able to just pull out, times sine of theta prime times z minus, well, I've used this already, I can clear some space. z minus r cosine theta prime over r squared plus z squared minus 2rz cosine theta prime to the 3/2 power. That is a big, ugly looking integral. Couple things to notice though. Nothing in here depends on phi, or phi prime rather. Nothing depends on phi prime. So this integral d phi prime actually can be replaced, integral d phi prime, all this is a constant and factors through it. That's just phi evaluated from 0 to 2 pi. So I can just replace this whole thing with, pen's dying again. I can replace this whole thing with just a 2 pi multiplying everything. So I'll get a 2 pi multiplying stuff out front. That's good. So I now just have the theta prime integral, but still you're probably looking at that theta prime integral and saying to yourself, what a horrific, disgusting, horrible integral this is. How the heck am I supposed to evaluate that? My answer is, I could tell you, but I'm not going to. Instead, what I want to do is just tell you what the answer comes out to be. Now, that's kind of cheating. I recognize that's kind of cheating, but you could just plug this into Wolfram Alpha or Maple or Mathematica or any number of places to actually do this integral. It's going to be better that way. So just plug it in. I could tell you later. I'll tell you how to do it. You can do a U substitution that makes this actually a really easy integral to do. But U substitution, we won't do it right now. We're just going to write down the answer. Let me copy down the answer from my notes here. This integral comes out to be sigma r squared, that was that constant we pulled out, over 2z squared epsilon naught. Notice that the pi's are canceled in this whole thing. And then what I end up getting is r plus z over the square root of r plus z squared minus r minus z over the square root of r minus z quantity squared. Okay. First thing to notice, let me write this down as a big, bold thing. Note that z is greater than 0, and of course r is greater than 0. So square root of something squared, that's just the absolute value of the thing we're looking at. So this is the absolute value of r plus z. If they're both positive, that means this first term is just r plus z divided by r plus z. So this is sigma r squared over 2z squared epsilon naught times 1. That's just that. This is the absolute value of r minus z. So this is minus r minus z over the absolute value of r minus z. That's an interesting construction. So there are two possibilities. If z is less than r, we'll get one answer. If z is greater than r, we'll get another. If z is less than r, then r minus z is positive, and this becomes 1 minus r minus z over r minus z, which is just 0 if z is less than r. Again, assuming positive z. If z is greater than r, then r minus z is negative, so the absolute value is actually z minus r. That means this comes out to 1 minus negative 1, in which case that's just 2. 1 plus 1 is 2. And this comes out to sigma r squared over z squared epsilon naught in that case. And let me point out, just for kicks, that sigma r squared over z squared epsilon naught could be rewritten, based on what we said the total charge was earlier. This is exactly equal to 4 pi sigma r squared over 4 pi epsilon naught z squared, or 1 over 4 pi epsilon naught times q over z squared. And this is the z component. So I could even say that E vector is equal to this times z hat if z is greater than r, and equals 0 if z is less than r. In other words, inside the shell, if we're inside the hollow shell, all the electric fields miraculously canceled out. If we're outside the hollow shell, by an even bigger miracle, all the electric fields outside act exactly as if the entire charge of the spherical shell was contained at a point in the very middle. That is what Coulomb's law tells us, and that's our result. With that, we'll stop, and I will talk to you later.